Welcome everybody again to another episode of the Idea Me Show, that show that profiles the humans behind the really big ideas that are shaping our world, inspiring the future and future creators. And for all those that like really great stories, I'm Ira Pastor, your life sciences ambassador along for the journey today. So today we are honored to be joined by Dr. Hugh Herr, who heads up the Biomechatronics group at the MIT Media Lab, also the Center for Extreme Bionics at MIT, and is basically in the process of creating bionic limbs that emulate the function of our natural limbs. In 2011, Time Magazine coined him the leader of the bionic age because of his revolutionary work in this emerging field of biomechatronics, which is basically defined as technology that marries human physiology with electromechanics. A double amputee himself, Dr. Herr is responsible for breakthrough advances in bionic limbs that provide greater mobility and new hope with those with physical disabilities. He is the author or co-author of more than 150 peer-reviewed papers and patents chronicling the science and technology behind these innovations. And these publications span the scientific fields of biomechanics, biologic motion control, as well as technological innovations of human rehabilitation, augmentation technologies. Dr. Herr's group has been involved in developing gait-adaptive knee prostheses for transfemoral amputees and variable impedance ankle foot orthoses for patients suffering from dropped foot, which is gait pathology caused by stroke, cerebral palsy, multiple sclerosis. He's also designed his own bionic limbs, the world's first bionic lower leg called the Biome ankle system. Dr. Herr has received numerous accolades for his groundbreaking inventions, including the 13th Annual Heinz Award for Technology, the Economy and Employment, the Prince Salman Award for Disability Research, the Smithsonian American Ingenuity Award. The list goes on. Dr. Herr's story has been told in a National Geographic film entitled Ascent, the story of Hugh Herr. He's also been featured on CNN and a variety of other broadcast media and many press. Dr. Herr earned his undergraduate degree in physics at Millerville University, a master's degree in mechanical engineering at MIT, followed by his PhD in biophysics from Harvard. Dr. Herr, thank you for taking the time out of your schedule to come talk to us for a little while.
I'm delighted to be here.
It's a real pleasure. Typically we start off this show by giving our guests the floor for a little while. If you could just, really take us back a little bit to the beginning, to you growing up nearby here in Lancaster, Pennsylvania, how you developed your sort of early passion for rock climbing, and a little bit towards sort of the fateful day in the early 1980s when you got caught on Mount Washington in a blizzard. I think that will really set the stage for a lot of what we're going to be talking about.
I started climbing, mountain climbing, when I was about 7 years old. My brothers and I, we began climbing in kind of mossy, steep cliffs along the Susquehanna River in southern Pennsylvania. But during the summers, my family traveled all over North America, Alaska, Utah, Alberta, all across the continental US, climbing steeper and steeper mountains and with very sheer rock and ice walls. I developed an extraordinary passion for climbing. In fact, when I was in my tweens, I was labeled as a child prodigy in the climbing world, climbing rock faces that no one had ever climbed before, let alone at my youthful age. And then the climbing became more and more severe, intense, more and more dangerous. And then when I was 17, I set out to climb the Huntington's Ravine on Mount Washington in January. And my partner and I, Jeff Batzer, were struck by an incredible storm high on the face. And what we intended to be a single day outing turned into nearly 4 days of pure survival. We were eventually rescued from the mountain, and we both suffered severe frostbite and hypothermia. And after months of effort, my medical team eventually gave up the hope to save my biological limbs, and both of my legs were amputated below the knee. So today I use artificial limbs, as was stated in your introduction, that are computer controlled and bionic.
When we think of I'm a child of the late 60s, early 70s. Obviously, I grew up with the U.S. television series $6 Million Man and the Bionic Woman, and I was exposed obviously at an early age to the term bionic. Could you just sort of take us on a little bit of sort of the journey of sort of how bionics and also if you just relate to biomechatronics, I'm looking at the definitions, they're slightly different, with biomechatronics involving more neuroscience and other aspects, I guess, of robotics and electrical engineering. Can you sort of walk us through the comparison between, or sort of they're used interchangeably nowadays, and then sort of, over the last 50 years, how this area, obviously you're a pioneer in the area now, but we heard about it decades before, was it something that slowly developed, where there fits and starts in it, because it seems like now there's a tremendous amount of activity going on in the general field.
The word bionic is a wonderful word. Unfortunately, it was stolen by Hollywood, and now we have all these images in our mind of what bionic is. The definition of bionics, and specifically human bionics, is typically the use of electromechanics merged with human physiology in a way that emulates nature, that emulates biology. And biomechatronics is within that same realm, the merging of biology with mechatronics for the purpose typically of some form of human augmentation, cognitive, emotional, physical, sensory experience, and so on. So you're right, this is an interesting time in the field of bionics. We now see a sufficient level of maturity in critical areas in science and technology, machine learning, tissue engineering, genetics, motor technologies, battery technologies. If you go across the spectrum, there's a level of maturity in each of these areas that is sufficient that if we in fact integrate these many areas of science and technology, we can usher in a really new era of bionics and a new era of what it means to be human, and what human capability is and how it can be in fact extended in very surprising ways.
I appreciate that. So in 2012, in the proceedings of the Royal Society, your biome system, was published. It was the first system that clinically showed that leg prosthetics had the ability to so-called normalize physiological function, allowing somebody with an amputation for the first time to sort of walk with a normal speed and a normal gait that was sort of inaccessible beforehand. Take us through some of that, if you would, and sort of what some of the challenges were prior to this period, with sort of thinking about sort of the underlying physiology that one has to adapt. One has some of these complex prostheses to learn to live with.
It may surprise some of your viewers, but walking is a very complex activity, and it's quite surprising that in my view, we don't deeply understand walking yet. It's something we all do, and we don't even think about it. But exactly what the muscles and tendons are doing and how they're controlled by the central nervous system is still being discovered, remarkably. So it was a tremendous accomplishment to emulate some of that complexity in using mechatronics in our 2012 publication. We were the first group to show that a mechatronic bionic prosthesis could emulate human walking. So we captured normative speeds, foot ankle dynamics, the metabolic cost required to walk. So quite remarkably, if you put a black box around a human being and you can only measure their walking speed and joint dynamics and how much food energy they're using, you can't tell whether the person has biological limbs or synthetic limbs. That's a remarkable accomplishment for science and technology. We have a very far way to go to emulate biological function across all that human legs do. walking, dancing, skipping, hiking, and so on. But at least for steady state walking on a flat surface, we have a start in the area of Binax. So how did we do that? We have a foot ankle device that has a muscle tendon-like actuator. There's a compliance structure that emulates the Achilles tendon. There's a motor that represents the calf muscle. And also there's computational intelligence that emulate the computations that are going on in circuits in the spinal cord. So we discovered scientifically how the calf muscle is controlled by the spinal cord using a positive force feedback. And we programmed the small computers, the small microprocessors on the device to control the motor in a way where the joint behaves as if it's powered by muscle tissue controlled by the central nervous system. So the device adapts in a natural way across speed variations and some modest levels of terrain variation.
And as far as you work on the biome system as a replacement, but you're also involved in exoskeleton work as well. And you mentioned, one of the areas that is extremely important in our understanding here. You're talking about sort of this metabolic cost, coming back to sort of concepts of using exoskeletons not just as a sort of replacement for something, spinal cord injury, but some of these rehabilitation indications, whether someone has had a stroke or early stages of MS. Talk a little bit about sort of the concept of metabolic cost when it comes to rehabilitating somebody as well as replacing something.
Yeah, so a prosthesis, a limb prosthesis replaces a limb that's no longer there. And then the term orthosis or exoskeleton is typically a mechatronic device that spans alongside the limb and parallel to the limb. And typically the word orthosis is used for a medical device that achieves that parallelism. And then exoskeleton is a device that augments. So a person that has limbs that do not have any type of condition would use an exoskeleton to actually augment their physicality beyond innate physiological levels. So my lab, you're correct, my lab is focused a great deal on both orthotic and exoskeletal development. We developed a powered computer-controlled ankle-foot orthosis that could be used for persons that suffered a stroke, for example, that have the classic drop foot pathology, where there's a muscle weakness in the front of the leg or the anterior compartment of the leg. We also were the first to develop an exoskeleton, a leg exoskeleton that actually augments normal human walking and running capability. So remarkably, scientists and technologists for over a century have envisioned exoskeletons that augment human walking and running. But all exoskeletons that were built prior to 2014 failed to do so. They slowed walking and running, increased the amount of energy to walk and run, basically very fancy exercise machine. And it was only in 2014 that my group showed scientifically that we could build an exoskeleton attached to a human and actually augment their ability to walk. A company has been spun out now called Defy, and we're actually at Defy, we are redefining what shoes are. We're making them exoskeleton and computer controlled and motorized to augment walking, running, and even jumping. So it's a very fun time.
I can imagine. Early, in your intro, you were mentioning some of what's coming, not too far out in the future, but some of these other applications. You mentioned things like machine learning and artificial intelligence. We recently, a couple months ago, we did a an episode with Dr. Alamandi over at DARPA, who's working on brain-computer interfaces. But one of the areas sort of in his portfolio at DARPA was this haptics portfolio, where they're looking at certain integrating components of the peripheral nervous system to sort of restore. What's that?
My group at MIT, we're a contributor to haptics.
Exactly. Can you talk a little bit about where you see sort of this haptic dimension going in terms of what we're seeing further out, as far as how somebody has a biome system or some of the other things that are becoming down the pike from your company, in terms of restoring sort of this sensation that, hey, I'm not just looking at this replacement, but wow, it feels like there's actually a real limb there.
We talked about the term bionic, which is using technology to emulate nature. Human bionics would be to emulate a part of the human body. The word cyborg is a term in which there is not necessarily an emulation of biology, but there's a link to the human nervous system, to a device, mechatronic device that's bidirectional. So in the prosthetic realm, a cyborg system would enable the user to think to affect the synthetic computation on the device, and also for that synthetic computation to input information into the nervous system to close the loop. This allows systems that the user can actually feel. So you can feed back as an afferent signal a cutaneous feedback, or the sense of touch, or a proprioceptive feedback, which tells us the position and speed and load on our joints. So we have frameworks now for both cutaneous and proprioceptive feedback, where we actually architect surgically and using regenerative medicine how the tissues are configured in the body to be conducive to a bidirectional neural interface to the prosthesis. So we actually have platforms where a person can think, move a mechatronic knee or an ankle, and feel that movement as a natural sensation. And actually being able to feed back signals like position or force from the prosthesis, which has never been done before. Our work with haptics merges a mechanical and electrical interface with the body. So we're pursuing an osseointegrated implant that goes into the bone of the residual limb. And that implant is hollow in its interior, wherein one can run wires from nerves and muscles inside the body through that titanium implant to the outside world, into the external prosthesis. So this is both a mechanical and neural port. You can actually see, as the titanium comes out through the skin, an electrical hookup, where you can hook right up into nerves and muscles, which is quite cool. So we're developing that system on the transfemoral level, or above the knee, but we have additional projects where we'll implement it below the knee as well as above the elbow. It's an incredible approach because it's clinically viable. Richard Brånemark, the pioneer in osseointegration, has performed hundreds of osseointegrated surgeries on persons throughout the world. So it's now a fairly stable interface. So it's exciting because a lot of these neural interfaces are not quite ready for prime time or clinical use. But the strategy we're pursuing can be clinically implemented right away.
Talk, if you would, just a little bit about this. It was recently in the news. You were cited as one of the experts in the arbitration going on with World Athletics, and sort of this burden of proof that was originally on disabled athletes to prove that their technology, the prostheses, didn't give them this unfair advantage, but this was invalidated. take us through a little bit, because I know this is happening right now, sort of as we're talking. It was just in the press a couple of days ago, but very interesting and exciting ruling, I would say.
Well, years and years ago, I was an expert witness on the Pistorius case. So Oscar Pistorius, a young man with a lot of athletic talent in the area of sprinting, started signing up to races against persons with, normal biological limbs. And he not only signed up for those races and competed, but began to win the races. And that got the attention of many people and many entities, including the IWF, the governing body of sporting events such as the Olympics. And the IWF did a very, very modest scientific investigation to try to answer the question whether Oscar Pistorius was augmented or not using these spring-like artificial limbs or running specific prostheses. And they, in a 2-week investigation, they concluded with very limited data that Oscar was in fact augmented, and they banned him from the Beijing Olympics. This got the attention of the community throughout the communities about the world, both in sports as well as policy and law. I was brought in as an expert witness when a law firm in New York offered to represent Pistorius on a pro bono basis. It went to court, to the Court of Arbitrators, and it was overturned, and Oscar Pistorius, as we all know, ended up competing in the London Olympics. Now, turning the dial forward in time, we have Blake Leeper. So it's kind of a Groundhog Day. So once again, I was brought in as an expert witness on Blake's case, and it's still ongoing. But the initial ruling is that he will not be able to compete in the Olympics that are coming up very soon. I disagree passionately with the ruling. And I think this general question will continue for some time. So remarkably, in this particular case, they used morphological data from persons largely from white and European communities to ban a person of African heritage. So I can go on and on. It's just quite remarkable, the ruling, but we fight another day.
So needless to say, you have quite a bit on your plate. You're clearly designing the future as we're discussing this with your orthoses, with the brain-computer interface concepts that are coming, and haptics. I still have to take out a little bit. Sci-fi ideas, things that you want to work on 10, 15 years from now. Obviously, Steve Austin had a bionic eye, and Jamie Lee, not Jamie Lee, but we had the bionic ear. Any sci-fi concepts that you sit around at night dreaming about when you're doing everything else you're doing?
What really fascinates me is what in the field we call embodiment, and I've been coining the phrase neurological embodiment. So there's a whole field on technological embodiment. So the classic example is a person with seeing impairment uses a cane, and the cane is therefore technologically embodied. But if you ask the person with seeing impairment that uses that cane, what is your body? Tell us how you view your body. They do not typically include the cane. A neurological embodiment, as a distinction, when you ask what is your body, the person includes the designed synthetic device as part of themselves. And my thesis is that this phenomenon of neurological embodiment and true ownership of a designed construct occurs when there's a cyborg functionality, when there's bidirectional bidirectional link between the mechatronic brain and the biological brain, that enables a person to feel, to sense that designed body part. When you can, if you can feel it, it becomes real, it becomes self. If you could feel your nose ring intimately, if you could feel your brace or even your automobile, it would become part of you, part of self, is my thesis. So we're beginning to see this in our prosthetic work. When we close the loop and a person can feel cutaneous and proprioceptive signals from the prosthesis, and they look down and they see the prosthesis obeying their motor commands. The people do and say remarkable things. The subjects say, I have my leg back. I have my body back. The artificial limb is part of me. And remarkably, we're now imaging the brain of these individuals with very powerful fMRI machines. And the brain representations, and using many different types of metrics, looks remarkably similar to the brain of a person with normal biological limbs. So as a thought experiment, if you were to amputate a limb, but if you were to maintain all the signaling in and out of the brain that was there before you amputated the normal biological limb, the brain wouldn't know that the limb had been amputated. Right? So if we, as time marches on in the field of neural interfacing, gets closer and closer to natural efferent afferent signaling in and out of the brain, the central brain will have normal representation. And what's remarkable is we're already seeing those behaviors in our central brain imaging projects.
Amazing.
What really excites me is a future in which we can sculpt human physiology. We can give a person a third arm, or give a person wings, or any type of anthropomorphic, even non-anthropomorphic structures. And those structures will not just be tools, but they'll be an integral part of natural physiology. And I believe in 100 years, humans will be unrecognizable from what we are today, morphologically and dynamically. And I also believe cognitively as well. So that's what excites me.
Doctor, one quick wrap-up question. We typically come back to you and pose a question about some of the important mentors and influencers that have been with you along this this path. Any specific folks that you may want to, obviously, you met a lot. Anyone specifically you want to shout out to, mention at this point in the discussion that really have either been with you or inspired you to keep going on this path when things were tough? Anyone you want to mention?
From an emotional perspective, my father. I was lying in the hospital. My legs had been amputated a few days before, and I very timidly expressed the dream of mountain climbing once again. And my father, in a very courageous way, I would say, stated to me, son, if you want to climb, do it. If you want to do it, you'll figure out a way, and you'll solve the problem. And just looking back today, imagine having a child and their legs were just amputated, and telling that child they can return and do something that's very, very hard from an athletic perspective. Most people would not do that for fear of that their child would be disappointed. So it turns out that I was able to climb, and remarkably, I was able to climb at a more advanced level after my accident with artificial limbs that I had achieved before the accident with biological limbs. So my father most certainly pushed me in the right direction.
It's been very inspiring. Wishing you the best with all this work, both on the academic side and the commercial side now. For everybody that's going to be watching this particular episode or listening on the various podcast networks, you've been listening to the amazing Dr. Hugh Herr, leader of the Bionic Age, head of the Biomechatronics Group at MIT Media Lab, also head of the Center for Extreme Bionics. Dr. Herr, thank you for taking the time out of your schedule to come talk to us for a little bit. Thank you for everything you've done and continue to do. And as we say, thank you for moving the human story forward a little bit into the future. It's really amazing stuff, and appreciating your time.
It was a delight to be a guest today.
Thanks so much.